At this point, we've seen that an electric field can be created by a changing magnetic field. And since electric fields give rise to differences in potential, we can think of a changing magnetic field as being a source of potential difference or a source of voltage. So in a sense, a changing magnetic field can act like a power supply, like a battery, for example. This voltage, or EMF, that's sort of created almost magically by a changing magnetic field is called an induced EMF. And in this lesson, we're going to take that idea and push it a bit further and look at a practical example of induced EMF and how it can be used to sort of generate electricity. We're also going to look at another way to think about induced EMF that in some situations can be a little simpler than applying Faraday's law like we did previously. But for now, let's stick with Faraday's law because that's what we're familiar with. And I'll just write it here as a quick reminder. So Faraday's law says that the induced EMF in a region, often a loop of wire or something like that, is negative N times the change in flux, magnetic flux, over the change in time. Now, this concept can be used to explain why current would flow in the following situation, where we have a conducting rod. So imagine this being made out of metal, for example, and it's being pulled to the right along two tracks or rails that are also conducting. So you can imagine them being made out of metal as well. And they're connected at the back here by a resistor. So applying Faraday's law and Lenz's law, we can sort of see what will happen in the situation. And note that all of this is happening with this magnetic field here kind of in the backdrop coming out of the page towards us. So as this rod moves to the right, we see that there's a loop here, a conducting loop. And the flux through that loop is going to change as we move that rod to the right. Right now, as you can see it, the flux through the loop is just sort of these dots here. Remember, I like to think about flux sometimes as the number of magnetic field lines. But as that rod moves to the right, these dots here will also be part of that loop. And then eventually these dots here will be part of that loop. So the magnetic flux is changing. I'm getting more and more magnetic flux. Or another way we can say it is I'm getting more dots. Now remember, any change in flux will cause an induced EMF. So this change in flux through that loop will cause an induced EMF in that loop that's going to try to counteract the change. This is Lenz's law. So if nature suddenly sees there's more dots through that loop, it's going to try to oppose that change. It's going to say, hey, how can I fight all these new dots that are being added? I'm going to try to create X's to balance them out. Remember, nature has no problem with there being dots there. If there were just a bunch of dots there and they were staying there, the same number of dots, that would be fine. Nature wouldn't have to respond. But it's the increase in dots that nature's going to fight by using X's, according to Lenz's law. So if this loop decides it wants to create some X's inside it to fight the increase in dots, it's going to do that by pushing current in the clockwise direction. So current is going to run this way through the loop. And you can verify that by using the first right-hand rule. We take your thumb and point it along any side of this loop, point it in the direction current is going, so clockwise. Then your fingers will wrap around that wire or that piece of the loop you're holding, and your fingers on the inside of the loop will be pointing into the screen, creating X's to fight the increase in dots. Okay, so by applying Faraday's law and Lenz's law, we've sort of determined that if I take this conducting rod and I move it to the right, I will get a current flowing in this loop in a clockwise direction. But there's another way to think about this. Rather than thinking of the EMF as coming from the whole loop, we can think of the EMF as coming from just the rod. And this can be nice because often when we think about electric circuits and electricity flowing in a loop, we like the power supply, the source of voltage, to be in like one particular place. We're used to seeing a battery or a power outlet or some sort of power supply at one point in the circuit. It can be a little weird to think about EMF as being sort of generated everywhere in the circuit magically by this change of magnetic field. It can be a little more satisfying to think of the EMF as sort of coming from one place in the circuit. In this case, I'll show you how you can think about the EMF as coming from that rod. So here's the logic. The rod, which is a conductor, has freely moving electrons in it. So we imagine lots and lots of electrons sort of scattered throughout this whole rod, and they're free to move around. As the rod is pulled to the right, its electrons will move with it. So this means we have moving charges, the electrons, in a magnetic field, and we can apply the second right-hand rule. So all the electrons in this rod will be moving to the right because I've literally just grabbed the rod and pulled it to the right. So all the electrons in it will come with it. So there's these electrons moving to the right in a magnetic field that already existed. That's where we're going to apply our second right-hand rule. So since these negative electrons are moving to the right, we're going to point our thumb to the left. Remember, the thumb goes in the direction of the current or the direction that positive charge would be moving. So if I have negative charge going right, my thumb goes left. Then we aim our pointer finger in the direction of the pre-existing magnetic field. In this case, it's out of the page. So I've got my thumb going left and my pointer finger coming out of the page or out of the screen. Now my middle finger, when I orient it to be perpendicular to both of my other fingers, is going to point up the screen or towards the top of the screen. This is the direction of the force exerted on the electrons by the magnetic field. So we've applied the second right-hand rule to say, what does the force look like on these electrons as I move this rod to the right? So if these electrons are being pushed towards the top of the page, they're going to be moving up this way, like that. That means that they're going to flow, when they get to kind of this intersection up here, they can't go to the right because there's no closed circuit over there, but they can go to the left, and they will, and they'll continue to flow around through that loop. So the electrons will flow through the loop in a counterclockwise direction. And since electrons are flowing counterclockwise, we would say the current is clockwise. So note, this is the exact same result as we got when we used Faraday's law. When we used Faraday's law, we said EMF was pushing current in the clockwise direction. And when we thought about this rod with these freely moving electrons and what the force on those electrons would be, we also determined there would be current in the clockwise direction. So we're getting the same conclusion here, but by thinking about this problem in two different ways. Now, the rod in our example is basically acting as a power source. When that rod's being pulled in that magnetic field, the electrons in it, the charges in it, are getting pushed and they're sent out into the circuit, which is exactly what a power source does. It pushes charges and sends them out into an electric circuit. So just like a battery, this rod will have a positive and a negative end, and there will be a voltage or an EMF between these ends that pushes current through the loop. I want you to think about this rod really like it's a battery. It's got a positive terminal and a negative terminal, and it's got a voltage. And now we can calculate that voltage, that EMF, with the following formula. E, or induced EMF in the rod, or in any moving conductor in a magnetic field, is V, B, L. And these guys all have to be perpendicular to each other. These symbols sort of clearly show that V and B should be perpendicular to each other, and B and L should be perpendicular to each other. What they don't really show is that L and V also have to be perpendicular to each other, but that is the case. So what's going on here? I have a conductor moving in a magnetic field, and it's going to have an induced EMF inside it. It's basically becoming a battery. So L is the length of the conductor in the magnetic field. B is the strength of that magnetic field. V is the speed, or how fast that conductor is moving through the magnetic field. And E is the result of all of this. It's the EMF that's induced in the conductor by that magnetic field as the conductor moves through it. And as I said, all of these need to be perpendicular to each other. So this formula allows us to think about a conductor moving in a magnetic field as basically being a battery, a power source that has a voltage, an EMF. Now remember, when we thought about this rod up here in that way, as being able to, as it moved through the magnetic field, push electrons up in this direction, we figured out that the current would be clockwise. And that was the exact same result as we got when we just used Faraday's law directly. Both this new way of thinking and the old way of thinking, Faraday's law, allowed us to conclude that the current was clockwise. Well, that sort of agreement carries through to this formula too. This formula really gives the same results as Faraday's law. In fact, we can show that this formula actually comes from Faraday's law. If I apply Faraday's law to a situation, I can get this formula, and that's what I'm going to show you right now. So let's start by writing Faraday's law. So induced EMF is number of loops times change in flux over change in time. Now, remember that flux, magnetic flux, is B times A, the magnetic field strength, times the area. So I can replace flux with B times A. And if B times A is changing, it's worth thinking about, well, why is it changing? Is it B that's changing, or is it A that's changing? And in this situation we had back here, the magnetic field wasn't changing. These dots were just here the whole time. What was changing was the area of this region, the area of this loop. As that rod moved to the right, that area increased. So we have a situation here where the reason B times A is changing is because A is changing. So I can rewrite this as B times delta A. Now, N is just going to be 1. We have a single loop here. We don't have a wire that's sort of coiled around many, many times. And this negative sign, remember, is just a reminder about Lenz's law. I don't even really keep the negative sign when I'm doing calculations of EMF. I just use it as a reminder that that EMF is going to try to induce a magnetic field that opposes whatever the change in flux was. So let's get rid of that N since it's 1, and let's get rid of that negative since it's really just about direction and not necessary for this calculation. So next I want to think a little bit about this delta A, and I want to write that in a different form. Here, just below us, down here on the screen, I've copied the same diagram we had before. But I'm just going to sketch it, just one aspect of it, one more time, right up here where I'm doing this work. So here's the loop. And here's the rod. And that rod is moving to the right. And we'll say, so a little while later, the rod's maybe going to be over here. So delta A is the change in area of the loop. The original area of the loop was just this here. And that area is always going to be there. But as the rod moves, there's going to be some new area that's added. And that new added area is this stuff in here. That is my delta A. And if we say that this whole, these rails are a distance of L apart, so the length from there to there is L, then it turns out we can write delta A in a kind of succinct way. Delta A is a rectangle. And the formula for a rectangle is length times width. So to find delta A, I just need to take this and multiply it by this. Well, that second one, that length is just delta L. And it turns out that this width here depends on how fast the rod is moving and how long it moves for. So speed is distance divided by time. So speed times time gives me this distance, how far the rod moves in a certain period of time. So V delta T times L should give me delta A. And I'm going to plug that into my, my formula that I'm working with over here. Instead of delta A, I'm going to write V delta T times L. And then I see that I have a couple of delta T's here. One that I just added on the top that's used to calculate my delta A, and one on the bottom that's from the original Faraday's law. Those guys are going to cancel out. And I get B, L, and V. Which is exactly the formula I just introduced you guys to up here, in a different order, but the order doesn't really matter. So, just as a quick reminder, what I'm trying to show here is that this formula is not really an entirely new idea. We can actually derive this formula by starting with Faraday's law, as we did down here. And that's the whole idea with this lesson. It's not a new concept, it's just a new way of thinking about Faraday's law, a new way of thinking about an old concept. So let's take our example again. Let's put some actual numbers into it, and let's try and solve it. So we have, let's say our conducting rod is 60 centimeters. So right here I've got 60 centimeters. And it's being moved at 5 meters per second. Across a magnetic field that has a strength of 0.4 Teslas. Along metal rails which are connected by a 3 ohm resistor, as shown below. If the rails are 35 centimeters apart, what are the magnitude and direction of the current through the resistor? Well, the whole point of this lesson, and the new way we want to think about this, is as if this conducting rod is acting like a battery, like a power source. As it moves through the magnetic field, it has a positive and a negative terminal, and it has a voltage, just like a regular power source would. So let's start by figuring out what our power source is, and then we can sort of solve the rest of the circuit to find some current. So, if we want to know what the voltage is of that moving rod of our power source, we're going to use our new formula. Now, it's always worth checking that these requirements, that all these things be perpendicular, are met. So let's double check that in our problem. I've got the length of my rod, L, which is going sort of up and down. I've got the speed, or the direction in which it's moving, which is going left, right. And then I've got the magnetic field, B, which is going into and out of the page. So one thing going up, down, one thing going left, right, one thing going into and out of the page. Indeed, those are all perpendicular directions. So that means I can go ahead and plug numbers in, and this equation will work nicely. But notice here there are a couple of options, or a couple of things you might think to write for L. There's this distance here between the rails, and there's this distance here from one end of the rod to the other. One is 35 and one is 60 centimeters. So in figuring out which one we should use, let's go back and look at what L actually meant. Well, L is the length of the conductor that's in the magnetic field. Well, I would say this whole conductor is in the magnetic field from there to there. It's all in the magnetic field. So I'm tempted to write that 60. But we're actually going to show both numbers. We're going to calculate it both ways, and I'll explain why in a moment. So we'll calculate it once with the 60 centimeters and once with the 35 centimeters. And the two numbers we get are 1.2 volts and 0.7 volts. Okay, so let's think about this. If I use the whole length of the conductor from the top to the bottom, I get 1.2 volts. But if I just use the part of the conductor that's between the rails from here to here, I get 0.7 volts. So which one's relevant to the problem I'm trying to find? Well, remember we can kind of think of potential or voltage as height on a landscape. And so one way we can kind of think of this rod is as a bit of a hill. It has sort of a low end and a high end. And as I go from one end to the other, from the low end to the high end, the voltage slowly increases. And the total difference between the low end and the high end is going to be 1.2 volts, or a height of 1.2. That's the difference between the two. But on that hill, if I were to not look at the whole hill, but 2 points on the hill, one that's a little bit higher than the bottom and one that's a little bit lower than the top, the difference between those 2 points would not be the full 1.2. It's only going to be 0.7. So again, thinking of this conductor as sort of a hill that has sort of a low voltage on one end and a high voltage on the other end, and as you go up the conductor, as you go up the hill, you get higher and higher voltage, or higher and higher potential. That can be a useful analogy here. Now, so then the rest of this circuit here sort of plugs into my conductor, plugs into my hill at a couple of points. Kind of like this is a slide that starts sort of high up on the hill and goes to lower down on the hill. Now, if I want to know the sort of potential energy I'm going to have going into this slide, it doesn't really matter how high the top of my hill is and how low the bottom of my hill is. All that matters is the height difference between where my slide starts and where my slide finishes. That's the part that's relevant to how exciting this slide ride is going to be, or how fast things are going to go down this slide. So yes, this whole conductor has a voltage of 1.2 volts. But because in this question, we're only interested in the current going through this resistor, we're only interested in the voltage that's actually connected to this circuit. And that voltage is just the voltage here between there and there, which is 0.35 or 0.7, volts. So So these are both legitimate voltages, but it's the second one that's going to be relevant for the problem we're trying to solve. So now I have a 0.7 volt power source connected to an electric circuit with a resistor in it. And I want to know the current through that resistor. So this becomes a very simple electric circuits problem, and we can apply Ohm's law. Or V equals IR. So because we're trying to find I, I'll rearrange. I equals V divided by R. And if I gain 0.7 volts in my power supply, I'm going to lose 0.7 volts going through that resistor. So the voltage in the resistor is 0.7. The resistance in the resistor is 3. So that gives me a current of 0.7 divided by 3, or 0.233 amps. Now, what about the direction that the current goes? Well, we've kind of done a pretty good job here of imagining this rod is a power supply and trying to figure out what its voltage is. But power supplies also have positive and negative terminals. Well, let's figure out which end would be the positive terminal and which end would be the negative terminal of this rod. So, right-hand rule, second right-hand rule. This rod has freely moving electrons in it. And they are moving to the right because the rod is getting dragged to the right. So negative electrons moving to the right, put your thumb going to the left. And this is all happening in a magnetic field that's coming out of the screen. So pointer finger goes out of the screen, and then your middle finger will point up the screen. That's the direction the electrons are getting pushed. So my electrons will get pushed up the screen towards the top part of the rod. So I end up with a bunch of electrons up here, meaning this will be negative. And because all the electrons are leaving the bottom of the rod, I'll have just protons left down here. So the bottom of the rod will be positive. So there we have the negative and positive terminal of this sort of moving rod power supply. And we can remember that current always leaves the positive terminal of a power supply. So current would head from the positive terminal this way, out around the circuit in that direction, and then it would come back to the negative terminal. So current is going clockwise or up through the resistor. And one other thing that I'll just maybe make a note of here is, again, this 0.7 volts. The reason we used that instead of the 1.2 is the 0.7 was the part that was actually connected to our circuit. The rest of that 1.2 was sort of overhanging on the top and the bottom, but not actually part of the loop, not part of the circuit. So the 1.2 volts here is for the entire rod. And the 0.7 was for the part connected to the circuit. So the key takeaway from today's lesson is that when you have a conductor moving in a magnetic field, it acts as a power supply. It develops a positive and a negative end. And it will have, between those two ends, it will have a voltage, which we can find using this formula here. And in addition to that, if once we find the positive and negative end, now once we find what its voltage is, if we then take it and hook it up to a circuit, just like any power supply, it will be able to drive current through that circuit, and we can find things like the current, etc., flowing in the circuit. Now, all of this, remember, comes from Faraday's law. It's not a new idea. It's just a new sort of packaging of Faraday's law, a new way to think about it that's particularly useful in applications that look like this.